it is time to mention a very important property that has been implicitly assumed until now. A property concerning not only the stochastic signal x of t, but also the stochastic process that has x of t as output. The property is called ergodicity, and the stochastic process is said to be ergodic. What does this property consist in? We have assumed that from these measurements in this time interval from 0 to t final in the continuous time case, or from 0 to n in the discrete time case, from these measurements, I was saying, of one stochastic signal, we can get information about the probability distribution of the stochastic process. So we are assuming two things. First, from this time interval, I can get information about the probability distribution for the entire stochastic signal. This means that the parameters of the probability distribution are always the same. In other words, that the probability distribution function is stationary. The probability distribution is always the same, the parameters are always the same, and thus, the larger this interval is, the better our estimates will be of the statistical properties of the probability distribution function. That is why we can assume this. This means that we are assuming a stationary process. But that is not all. We are also assuming that from this time interval of one stochastic signal, we can find things about the stochastic process itself. Perhaps you remember that I said that very often, instead of representing the stochastic process like this, we simply use this, thus implicitly saying that each particular stochastic signal that is output of the stochastic process can be used to find all that there is to know about the probability distribution of all the stochastic signals that are outputs of this stochastic process. Not all stochastic processes are ergodic. Let me give you an example. Suppose that x of t is given by a sine of t plus theta. T is the time, this is the amplitude, this is the phase. A and theta are random variables. They are constant for each particular stochastic signal that is output of this stochastic process. But each time that we run, so to say, this stochastic process, each time that we carry out a new experiment, we'll have a new value of A and a new value of theta. Consequently, if we run this once and we find something like this, we can measure A and we can measure the phase theta. Actually, we are in a situation in which there is no randomness. We are in a situation which is actually deterministic. But since A and theta will change each time that a new experiment is obtained, we can measure this particular stochastic signal for as long as we want. We'll have no information that will let us know that the next time we can have a completely different phase and a completely different amplitude. Of course, from several different stochastic signals that are outputs of this stochastic process, we could get a statistical characterization of A and theta. But, as I said, from only one stochastic signal, which is output of the process, we cannot find the important statistical characterization of the entire process. We would need several stochastic signals rather than a long interval from only one stochastic signal. So we will always, in what follows, presume that stochastic processes are ergodic. So we will always presume that from a sufficiently long time interval, from only one stochastic signal, we can obtain the mean which is a good estimate of the expected value, that we can also find values for the variance and so on and so forth. Let me mention that it is possible, if our probability distribution is not stationary but only quasi-stationary, take measurements just the same. What we have to do, if we are in a quasi-stationary situation, that is to say, if the parameters of the probability distribution change, but change very slowly with time, what we have to do is to measure up to a certain interval, and from then on keep the width of the interval constant, discarding old measurements and only using the most recent measurements with this constant interval floating, so to say, with time, just as a moving average, for instance. In those cases, we can cope with quasi-stationary probability distributions. However, as I said, in what follows, we will always presume ergodicity and hence also stationarity.